Yeah, okay.
Good afternoon, everyone, and welcome to this. Good afternoon, everyone, and welcome to this special asset curriculum. I want to apologize for a slight time scheduling thing which had to be done last minute. So instead of 11 morning, we have to convene at 2:30. So I apologize for any inconvenience of somebody came here and then they had to realize that it wasn't there at this time. So we are here to hear from Professor Karan Jani, and I'm sure it is going to be a very interesting talk. I request Lupu to introduce the speaker formally before we start.
Thanks a lot, Karan. I think I should apologize because actually I created all this confusion. I know that Joe and many others came at 11:30 for the talk. Thanks again for coming. It's a really great pleasure to have Karan Jani visiting us actually for a few hours today. So Karan is one of these young, brilliant professors of Indian origin in the US. So he's currently at the Vanderbilt and he's the director of Vanderbilt Lunar Lab Initiative. So Karan did his PhD from Georgia Tech, and 10 years ago we started kind of chatting a lot in the name of gravitational wave detection. He did this thankless job of coherent wave burst significance and the numerical relativity simulation for the first event. We were kind of chatting about the eccentricity, this, that, and all that. And then he stayed there for a postdoc and then moved to Vanderbilt, and he has been there as a professor for the last few years. And hopefully we will see you here for a few months next year. And then, so he has been driving this idea about an LIGO kind of interferometer for gravitational wave observatory in Moon, and we'll see the advantage of that. It's a very ambitious program, and imagine 50 years ago, LIGO was precisely like that. And as his close collaborator was mentioning, maybe within his lifetime, he may be actually analyzing the data itself. So it's an amazing. So Karan is interested in various aspects of gravitational wave astronomy, this being one, but in numerical relativity, data analysis, and then astrophysical implication with a wide variety of collaborators. We keep talking about each other. Yeah, right. Sometimes there's some point of time. So without further ado, on to Karan. Thank you.
Thank you. Well, thank you. Thank you, Thank you, Gopu, for inviting me here on a rather short notice. So in terms of apologies, I should also apologize that I made the schedule pretty tight for Gopu to have this visit schedule. It's always an honor to be here at the IFR. It's been a while. I think the last time I came was in the pre-pandemic era. So some of you are new faces, and I've been very glad to have a discussion with you all. The thing that I'm going to talk about today, it's on a rather sort of informal sort of, just giving you a state of the field, A, where we are as the field of gravitational waves, and B, where we are as a field trying to go next now that we've already made discoveries in gravitational waves, right? So take this as a sort of, quick recap or review of where things we are trying to do. I chose this one specific topic because of the large interest that we, and especially in India, there is this interest for lunar-based science or the lunar landers. I do work on other things. This is a small fraction of the time that has now been my completely devoted in whatever time is left as a faculty. So my group here, this is my group. We are 4 postdocs, 6 graduate students, communication specialists, and primarily our effort is between the 2 flagship ideas that we have in gravitational wave community right now. The one is the LIGO Virgo Kagra collaboration. I have colleagues here, Sudeep is part, and Gopu is part of this collaborations. There is also an upcoming space mission, LISA, which is the next big frontier in our field. I'll speak a little bit about it. And the third is then we are already starting to think about it takes generations to build one gravitational wave detector. So what is the next sort of big frontier after, this mega missions are happening? This is also an advertise, we are a very expanding group at Vanderbilt in multi-messenger astronomy. We are in Nashville, Tennessee. We are famous for being the capital of country music. And also if you heard of Jack Daniels whiskey, that also comes from the state of Tennessee. We are covering all the bands of gravitational wave spectrum. So students, postdocs who are interested, please absolutely do reach out to me about that. The current Earth-based network, and apologies if it's a summary for some of you in the field already, consists of primarily the two LIGO detectors that are both in the United States. And then there is an additional detector, Virgo, in Italy, and the one Kagura in Japan. So this forms what we call the current Earth-based gravitational wave network. And then by somewhere in 2030s, we would have another addition to the gravitational wave network, which would be the LIGO India. All of them fundamentally operate on the same principle of discovering gravitational waves through the technique of interferometry. So when incoming gravitational wave stretches the space, we are trying to measure that. The next frontier in the field, which would come in mid 2030s, now it's like pretty at a significant stage. This is not something that is if and or based on funding. This is absolutely happening, which is the space mission LISA, Laser Interferometer Space Antenna, which would consist of, this is a old PR video, so I apologize, it's not really updated. But the real success that we know that we can make a space mission happen, you can essentially think a LIGO in space possible because of the success of what was the LISA Pathfinder that only happened to exactly show the result at the same time when we had the first discovery of gravitational waves. It's very timely. The LISA mission is very complex. It is I would call it the largest astronomy space telescope to be ever built. There is nothing in comparison with the LISA space mission. It would be 3 satellites that would be orbiting the sun. It would be trailing behind the Earth, and it essentially is the 3 end stations you can think of LIGO would be doing interferometry. Now, taking back a little history, so this is all great. This is what we are trying to pursue now. Next, we have LIGO India very much, decided to start. Then we have the space mission. The first gravitational wave detector, actually, outside Earth, happened in the year 1972. It was called the Lunar Surface Gravimeter. And the PI of this project is the founding figure of experimental gravitational physics, Joe Weber, who was at the time at Maryland. This is also the last time that humans had landed on the moon. This was the Apollo 17 mission. And it carried with them this detector that Weber had built. This is actually the synopsis from the NASA's pages of what this instrument was going to do back in 1972, that the primary objective is to use moon as an instrumental antenna to detect gravitational waves created by Einstein's general theory of relativity. And gravitational waves carry energy, momentum, and information concerning changes in the configuration of the source. It's a very accurate picture of what we were trying to do. Now, the instrument did not work. Otherwise, we would have had the field much more matured by 2024 if we had made the first detection in 1972. And there were 2 reasons for it. One was the instrument actually was damaged by the manufacturer before it actually went to the moon. And the second was, in principle, the way Weber thought about gravitational waves is not the way we currently think are measurable gravitational waves. So the idea Weber had was the entire moon would stretch and be in resonance with the gravitational waves. And then this would be used as a way to measure the vertical acceleration of the moon and trying to cancel the seismic effect local to the moon with something which was extraterrestrial. And it was a very brave idea. And more importantly, it was fundable. Because even in 1972, they were convinced that detecting gravitational waves on the moon is actually not as ambitious or crazy as it sounds at first. Right, so then move ahead 400 60 Mondays ago, on September 14, 2015, we finally made the first discovery of gravitational waves, the signal famous now called the GW5914. This is the first direct detection of gravitational waves. The way to look at this plot is we typically plot the raw data of LIGO in this spectrogram of frequency and time. So this particular shape you see corresponds to what we call the chirping sounds of black holes. If you convert this into wave domain, you would see this very nice chirpy signal that increasing sinusoidal. If you take Einstein's field equations, solve them as a two-body problem, which is the case for two black holes, and look for the perturbations in space-time in one direction, then you try to reconstruct the waveform, it matches this exact shape. And that is how, in a manner of speaking, we know that the detected signal is not only consistent with Einstein's theory, but it is consistent with the concept of black holes that are predicted in Einstein's theory, right? And we did that in the first detection with a lot of care. And since then, we have seen now so many gravitational wave events that it is really hard to keep really track of which event we are talking about. When I finished my PhD, I was very happy that I had 3 gravitational wave events to write about in the thesis. One of them was actually a candidate, was not confirmed gravitational waves. In my postdoctoral years, we saw another 10 events, about total 11 events. And that was like, wow, we have now 11 events, including a very famous signal where gravitational waves and light were seen together. Right since I was joined Vanderbilt, this is the number of events that we have seen only in the third observing run that actually ended in 2019, a little earlier, sorry, 2020, a little earlier because of COVID. This is our entire public catalog, what we call the gravitational wave transient catalog. This image was the NASA's astronomy picture of the day, which made me really happy. I made with one of the graduate students, Sudarshan Ghonge, because these things were always considered fundamental physics, detecting gravitational waves. And the fact that now this is equivalent of what you consider light being recorded by something like JWST or Hubble is really shows how the field has matured over the years. Since the fourth observing run has started last year, if you go online and look at how many alerts we have sent out to astronomers and have not retracted them, which is a hint that these are real gravitational wave events, they are already more than all the total events that we had seen so far between first 3 observing run. And that is only the first half of the 4th observing run that has started last year. It is still ongoing. By the time we end this observing, I mean the 404B, which is the second part of the 4th observing run is going on, we'll see equal amount of events. By the end of next year, you would have a catalog of 350 gravitational wave events. This is essentially equal to what exoplanet community had went through over the years, right? You had few first detection, and after that, boom, you have just series of number of events that you can do astronomy with. By the end of this decade, by the end of this decade, the number will reach 1,000. By the end of next decade, there will be tens and tens of thousands, right? So that is the scale at which exponentially the field number of detections are increasing. However, even after this magnificent success that our field has had, which has no parallels in modern astronomy or physics, there are still mysteries that seems to be completely unsolved. One of them is the fact that we started detecting, and we now have a few of this, black holes which are about 150 solar mass or greater. Now, by themselves, this number doesn't mean much because we know black holes can be millions or millions of solar mass. But the fact that the smaller black holes coming directly out of stars are very difficult to make, about 90 and 60 solar mass, which collides to make something around 150 solar mass. And it's very difficult to think from stellar evolution alone at how these black holes are being created. So the origin story, even after several of this, has been completely unknown. And the second that has been a rather less of a surprise, but more of a sort of pessimistic sense that we have only seen one multi-messenger event so far. Right? So the promise of gravitational waves has always been you are seeing sources which may also emit light, and then you'll be able to make a joint detection, just like it was imagined that neutrinos and electromagnetic astronomy can work together, the same way electromagnetic astronomy and gravitational wave astronomy can work together. But it has only happened once. And now we have seen a close to 150 events, and that has still not been a single credible interval, except in the first time that we made the discovery. And the reason for both, if you want to just ask from a perspective of our detection selection effect, is that the detectors that we have made cannot see gravitational waves below 10 hertz. It's just a fundamental limitation of how we do gravitational wave astronomy on Earth, that is we are doing right now. So, yeah, 20 hertz is being very ambitious. And it is not so simple that to make detectors work at low frequencies. So I have actually, I'm just going to go, yeah, this plot. I'll come back to the old plot. This is LIGO that was operating in 2009. This curve, the way to think about this curve is the x-axis is your frequency of gravitational waves. It's the same way that we look at electromagnetic frequencies. And the y-axis is this characteristic strain, is how much it stretches the detector. The initial LIGO, as Gopu just mentioned, like anything even less than 50 hertz would have been really impossible to measure. And that is why when LIGO ran from 2000 to 2009, we did not make any confident gravitational detection because we simply did not have the sensitivity at low frequencies to capture the signal long enough that it stays in our band for us to do data analysis. Right? It was never that significant event. LIGO right now in 2024 is this blue line. And you can just see the improvement that we have moved at least by a factor of 5 down in the low frequency, and we have also improved almost by an order of magnitude in the frequency below. And that's the fundamental reason why we see with the same experiment so many gravitational waves. But 10 years or 15 years ago, the same experiment was not seeing that many gravitational waves. And in between, there has been series of course, upgrades that have led to make this happen. If you want to cross 10 hertz barrier, it's extremely challenging on Earth because you reach a point where the Earth itself is vibrating. And that's why you cannot make the signal stand out against the background noise, the humming of the Earth that it exists. Let me go back now to the slide that I missed. You can think of gravitational wave spectrum the same way we think of the electromagnetic spectrum. So LIGO or LIGO kind of detectors, LIGO India, Kagra, are what you would call a high energy X-ray telescope. These are short bursts of high energy that we end up observing. The space mission LISA that I just talked about are rather low millihertz period signal. LIGO operates as hundreds of hertz. LISA operates at about millihertz frequency. And then pulsar timing, which has been a big effort from India. Gopu and others have had this very major announcement last summer, is at the nanohertz. So that's even further. So this nanohertz is equivalent to what I would call the radio band of electromagnetic astronomy. LISA meaning more, I would say, infrared. And then there is this missing band where neither Earth-based or space-based detectors can measure gravitational wave right now. For the purpose of analogy, think of that as the visible light. Right? Imagine we have not seen the entire universe in visible light. That is exactly where we are as a field right now. We are not able to see this one full band. And not just now, we don't have any sort of a plan right now for at least the next 20 years to cover this spectrum. The universe is rather pretty rich in this frequency spectrum. I have, there are a series of sources that can only happen in this, what we call the sub-hertz band, which is less than 1 hertz. Those sources allow a certain test of general relativity that you otherwise cannot do in either of this band. I have this poster that actually summarizes all the sources. For example, one of my favorite is the mergers of the white dwarfs that lead to type 1a supernova that can only happen in this particular frequency band. There are multi-messenger tidal disruption events that you don't see by any ground-based detectors, right? So there is a whole series of things that you can end up doing there. The other thing is that in between, the two problems that we have, that we cannot see enough binary neutron star multi-messenger, neither we know the origins of black holes, neither of that is being solved by LISA. Because LISA is so low frequency that none of the sources really make the cut for to be detectable in human timescale. And LISA by itself is a space mission with only about 4 years of mission lifetime. So the question. Yes.
4 to 5 years. It's like we know they're going to march 5 years down the lane in the, say, NVIDIA or CET band. So the multi-messenger side, I agree that we will get a large reward of time.
Yeah.
For the LISA side, I think of the heavy mass and the mass gap or second generation black holes, we have a potential chance of catching them from LISA as well.
Very rare. So, sorry, I was just going to highlight. So this is this paper, the gravitational wave. This is the paper that made the cover of Nature Astronomy, where we talked about all the multi-band sources that LISA would see. Now, the problem with 190521, like this heavy mass, is that their merger rate is 500 times rarer than stellar black holes. So with the 4-year LISA lifetime, we are left with only 1 or 5-ish, type of total source. It is true that we may have a handful of lucky detections, but not so significant. That can solve, this underlying formation problem.
Mid-band detection for more than 10 years of frequency?
So just LISA and LIGO alone will not be enough. Right? So mid-band, yes. Mid-band would help. Yes.
If 1901 carrying eccentricity or something like that, you are in big trouble because it passes through very these are
yes.
Chances of missing it.
We may end up seeing some stellar at low SNR, but let's say if we just took 190521, at that distance, LISA would not even see it. So you would only see that signal if it was at 1 gigaparsec, which drops the rate to about 0.01 per year. And that means in a 10-year LISA mission, you have only maybe 1%, 10% chance of seeing such a source.
How does the frequency related to the source?
How does? Yes, so it scales inversely with the mass of the source. So if we think about neutron star mergers, which are the lightest sources, which are 1.4 solar mass plus 1.4, they merge at around kilohertz. Versus if you talk about mergers of galaxies, like million solar mass plus million, then they would happen at millihertz. So it's just simply the scaling with the masses that's taking place. And then there is inherent time scale, how far they are from merger. So the same source that is merging in LIGO, it is at the end of its evolution as a binary, but it has lived millions of years and has been emitting lower frequency gravitational waves. Right? Weaker, but lower. So there has been plans actually to fill up the mid-band detector. You can broadly classify into 4 technology that allows you to do it. There is a review article that we published in this one of this handbook of gravitational wave astronomy, which is a great, by the way, resource for graduate students who wants to know about the state of the field. You can think of making a LISA-like detector in future, which is a space mission that can access the subhertz gravitational waves. The current plans that we have to have those kind of technologies to even allow it is very unlikely to exist even till 2050, right? As a post-LISA mission, maybe we can start thinking about it, but this is still very far out from a technological perspective. The second option is to think about a geocentric mission, like let's say a bunch of CubeSats. Can they make a measurement of gravitational waves? It may not be that accurate, but can it detect gravitational waves? In principle, yes, but it's very hard to keep them stable enough to make a measurement that is significant in sensitivity where we can claim a gravitational wave detection. The farthest right is the atom interferometry. I'm not part of this community, and they have generally been, fundamentally different origins on how they have approached this problem. But they are working on that, you can use atoms instead of lasers to conduct interferometry, and that can solve the midband. And that approach also requires you to have a space-based detector by design. The one that I do want to stress about, which is a more recent kid on the block, is this lunar-based gravitational wave detectors. And there are essentially two approaches where there is a major community-led effort. One is from the US side, which I'll talk about today, which is LILA. And there is another effort from the European side, which is called the LGWA. So those are the two main efforts that fill this mid-band frequencies. Yes, yes. Yeah, sorry. I mean, the PI is at Europe. I should clarify. The PI is at Europe, and the PI is at, even we have enough European collaborators, so they would not be happy about it. Now, why build a laser interferometer on the moon, right? So first thing is that the moon is seismically, as we understand, is at least 10,000 times quieter in the frequencies where we want to discover gravitational waves, right? So that is a very major push that we, unlike on Earth, where we have to go to great length to isolate the seismic noise so that we can make a gravitational detector, the moon naturally offers us that. The second is that the natural vacuum on the lunar surface, and specifically around the crater, is 2 orders of magnitude or even more sharper than the ultra-high vacuum that we have implemented in LIGO. Those would be built for LIGO India or any future ground-based detectors, right? So the moon is already more sort of naturally suitable. And more importantly, at least as of now, there is no environmental noise or human-created noise that is being caused. There are no heavy machineries. There is no anthropic noise that is being caused just because of the motion around it. So if you use these 3 things, which we know actually since the Apollo era, that is not new, one can already create an idea that, oh, how would a gravitational detector on the moon would look like? And actually, it was thought by the leaders of the field back in 70s and 80s when NASA was at the time serious about thinking about what is the future on the moon, even after the Apollo missions had ended. There's this very nice early papers by Stebbins and Bender and Peter Salson, etc., who looked at the idea of what would be the noise curve on the moon. So pressing now in the year 2024 is that there is a complete rejuvenation of what we think about the program to moon is going to be. This is all the missions that NASA is sending or has sent to the moon between 20 up to 2025. One of them is just the orbital missions that would be orbiting around the moon, and the second are the surface mission that would be soft landing on the moon. A point to note is none of these missions are actually led by NASA. These are all private companies which are making the missions, that are leading it. The launch is by a private company, the landers is by a private companies. It carries scientific payloads which are from academia or from research institutes, but the entire process is completely led by private companies. And this is a very different shift at how we are looking at returning back to the moon, right? This is not those kind of Apollo era where it was extremely heavy engineered to not fail. These are much lighter missions if you want to think about. The second idea why they want to push the private industries to demonstrate a routine launch to the moon, and not just launch, but also a soft landing on the moon, is because of the ambitious Artemis program that aims to land the first woman and the first person of color to the moon by the year 2026. Which is a very major effort now back that, we want to send astronauts back to the moon. We want to have a sort of a habitable space in a way that astronauts can return back again and again to that place, just like how International Space Station became such a thing in 90s. So this whole effort, the Artemis, is now the significance of what I would call the NASA Artemis, NASA's entire yearly budget. So just the year 2025, the Artemis campaign, which is return to the moon, is about close to $8 billion, right? So that is just the amount of investment that is going to go into the research and science that is unique to the moon. Furthermore, there is an additional $1 billion portfolio just for the space technology development that NASA is interested specifically for the Artemis base. Now, if you compare that with astrophysics, and we've had some of the great missions in past, we have had James Webb Space Telescope, we have Roman lined up, several of them. There is no significant increase in astrophysics budget now for us to ask for more ambitious space missions for astronomy. And that is where I see there is a real key here, that we are not going to the moon to detect gravitational waves. We are piggybacking on the fact that the large resources are already going to be invested on the moon, and how we as a physics and astronomy community can take an advantage of these resources that are being pulled. And this is not just on papers or white paper, this is actually happening. These are the few soft landing pictures I've taken that have happened this decade, so in the last 4 years. These are all real pictures. I was very particularly not to take any simulated or a photoshopped image. This is the Chang'e lander that went on the far side of the moon. This is the first soft landing that has happened in the far side by China in 2020. This is, of course, a very proud moment for us when the Chandrayaan-3 landed near the lunar South Pole in 2023. Then this is the JAXA mission that actually landed upside down, but it's still a soft landing, and it didn't crash land. So this is pretty significant, as it was the first time. So you can see this is also an actual photograph. And then the first one this year, sorry, it's not initiative machine, it's intuitive machines. Auto-corrected me. But it's the first soft landing on the moon by a private company. So Intuitive landed sometime, I believe, in February. It actually landed, one of the legs landed on the rock. So it soft landed, but then it kind of tripped a little. But it was actually carrying a radio astronomy device to make an exoplanet observation of the Earth from the moon, just like an alien species, let's say perhaps like us, would be doing for another planet. It still carried a significant scientifically interesting payloads. Now, all this has happened just in a couple of years. And one can sort of scale it and imagine that the ambition that we have to land humans on the moon, to give a perspective here, the lander of Chandrayaan is about 1,800 kilograms with about 200 or 300 kilograms of scientific payloads. If you take the cost of Chandrayaan and divide per kilogram, it is not a significant amount of cost to send something to the moon now. And that's the true even with the nature of private companies. It takes about give and take a couple of $100,000 per kilogram to send to the moon right now. But if you have 50, 100 launches that are happening within this decade, the price would at least drop by a factor of 10, right? That's the hope.
And China has recently landed different ones.
Yes, they have done 3 landing and all 3 successful, with one of them also being a sample return. Yeah. Oh, I do not know. That's okay.
And it's supposed to have 100 launches to moon by the end of this decade. All of it.
And I mean, even from the India side, I mean, the plans are to have an Indian astronaut on the moon by 2040s, which seems consistent with the technology timescale at which, how things are evolving. So all that given, yes, good.
Having laser interferometer in the moon is helpful because there are no human contamination, but aren't like what they're getting at.
It is. If we all cramp at the same place, I mean, the moon is still pretty big. These are small toy cars, if not even smaller, in the spaces that we are occupying. This is not heavy drilling yet, heavy machineries yet. Not that it's too far in the future, and I'll come back to that. We have plans to protect the moon for that. So with all the efforts that are happening, the sort of the community has combined towards this effort, which we call the laser interferometer lunar antenna. which I call Leela. Some call Lila, but that's why I correct them. That is really the Indian word Leela. The idea then is that how can we take what is the simplest modification you can do to a LIGO kind of interferometry, put it on the moon, and make it work for gravitational wave detection, right? Now, this is a sort of an ongoing concept that is being evolved with by the community, but I can give you a rough estimate of, so if you take a crater that is roughly 10 kilometer in diameter, and we have to pick a crater because the moon's curvature takes over after 2 kilometers. So if you take a crater, you put the 3 ham stations, what we call in LIGO, which host essential optics that allows us to make the measurement, which is the test mass and the laser set. Have it at 3 distances of about 10 kilometers. Each by itself is a couple of 100 kilogram payload itself. That setup allows us to make a measurement in gravitational waves exactly in between the LIGO and the LISA band. Right? So this is our preliminary target that we want to make not only go up to about a hertz, but we want to go less than a hertz in the sub-hertz, about 0.1 hertz regime. Right? So this is our sort of science case, that a new frequency that is being opened in gravitational wave spectrum that you cannot see otherwise from Earth or from space. The direct effect then it happens that it expands your multi-messenger landscape. I already talked about the white dwarf mergers. You could also have these tidal disruption events, which are another source of multi-messenger. So the problem right now is that we have only one category of multi-messenger, essentially, which is the binary neutron star merger. The universe offers many different scenarios where gravitational waves and electromagnetic signals are emitted together, and we start seeing that kind of a band in between the space and the Earth-based detectors.
Why the TDI should be instead of not the
Why the tidal disruption? It will be, but not from intermediate mass black holes. You could have this white dwarf and IMBH, which are of comparable size in terms of the radius. And that is very unique to that IMBH mass. The case that has pretty much excited the community. Yes, go ahead.
It can somehow modify the distance between the three laser stations. Can we in principle trace the different spectrum of
No, the problem with LISA is that it is a free-floating satellite, unlike here, which is a suspended test mass. So if you bring them closer, the photon shot noise causes a residual acceleration to the satellites. So that itself does not allow us to go to high frequency. So that's why LISA really tails off. Right? So simply, if you're bringing them down, you have to decrease the noise by almost like some 10,000 times. Right? Yes. And our arm length is really a choice of what are our typical craters on the moon, right? So that we can essentially access. So the science case that is really exciting to the community is that if you had this binary neutron star, which we have only seen one, if you had Leela operating at 0.1 hertz, which is our target sensitivity range, you would see the binary neutron stars 6 years before they are going to merge, which completely changes how we think about multi-messenger follow-ups. That means 6 years ago, I can predict, not 6 years, but at least in a couple of years after the signal has collected, where in the sky the signal is going to come from, at what second that the merger is going to take place. Even if Leela does not reach its target sensitivity in the first phase, even if you have a 1 hertz, which is a very pessimistic design sensitivity for Leela, even then you have a 5 days of heads up of where the signal is going to come from in the sky. The advantage that it has in sky localization is that if you had this 1 month or couple of years of heads up, the moon only takes about a month to finish an orbit around the Earth. So now you have several cycles that you can use at your advantage to trace where the signal is being Doppler shifted from, which in turn for a source like binary neutron star brings it to close to a couple of arc seconds square. That even without electromagnetic astronomy, you can, at least in the local universe scales, know which galaxy the direct association is happening. And then, of course, the same holds for a heavy solar mass black holes. But of course, the sensitivity starts dropping in how well in the sky you can do. Now, compare that with any modern combination of measuring binary neutron star, whether you have LIGO India, whether you have a third generation detector. This is a orders of magnitude much deeper effect. Yes. Yeah, so it's by construction. It's not that we are specifically fine-tuning it to make this measurement, but the frequency offers us this kind of rich science. Another case that is I'm pretty excited about is how far in the universe can Leela survey certain kind of black holes. If you take this a different view of looking at the boundary of the universe, so the upper boundary here is your cosmic microwave background. And then each concentric circles is the percentage of the observable volume of the universe covered inside. If you look at LIGO right now and ask how far in the universe can LIGO see, it is within this small circle. And that is the entire range that LIGO has seen, all binary black hole mergers till date. When a third generation detector on the next generation detector like LISA comes in, the space mission, it would start seeing million solar mass like Milky Way like galaxies merging all the way up to redshifts of 20. Now we definitely would not be seeing galaxy mergers that early in the universe, but the fact that the detector is sensitive that far in the universe. If there is anything merging, which would be a strict violation of lambda CDM, it would be able to catch it. But it does only at the high mass ranges, at about million, at best 10,000 solar mass. What Leela offers is it can see at the same distances as 100 solar mass black holes, 1,000 solar mass black holes. Now, they cannot be coming out of simple stellar evolution processes so early in the universe, but they could be your key to testing the seed formation for galaxies. It could be also tracking primordial black hole population early on of this, hundreds of solar mass black holes. That otherwise you cannot offer from any other detector, right? So that is particularly an interesting thing here. I think that may have been interesting for Sudip was the dark energy we can measure in 4 different ways on the moon, which is very unique, and there is no other experiment that I can think of that is the 4 independent tracks of measuring dark energy. One is simply by measuring mergers of white dwarfs. If they are progenitors to type 1a supernova, you can measure the chirp mass so well with gravitational wave observation. You can directly link with the luminosity. Any deviation in the luminosity, you would have it correlated with the chirp mass of the binary. So you can use that as a calibration technique. You would also have, even if it's a single degenerate channel that a star has collapsed to form type 1a, that gravitational wave emission also happens about hertz, 1 hertz. So you can even use that as a standalone measurement for calibration of errors. And then the other things are what LIGO already does, but we do it, orders of magnitude much more profound. About 100 megaparsec. Yeah, much more. I mean, you would see. So which means that essentially you can calibrate the peak of the curve like where we miss. Yes. Now, before we go and build the whole gravitational wave detector, we would, of course, have to do series of technology demonstration on the moon, which should be prone to, testing. We still have a standalone science case. Now, one of the things that has excited the geoscience community about this process is that the strain meter that we build between several kilometers allows them to make an accurate map of the lunar interior better than any seismometers just keeping it around an array is able to do. This is just a plot of how much the strain amplitude is been measured by the device, and so far everything we have sent on the moon, it has been fundamentally limited by the self noise of the instrument because the moon is quieter than that. So this is what the Apollo noise curve blue line was. The green line is what the next generation interferometers that have been selected to go to the moon. The red line is what the Leela Pathfinder mission, where we essentially have just two end stations separated by a few kilometers trying to make an interferometer will have, right? So this is very exciting to the geoscience community. And that's all actually I know about the geoscience goals here. We are a growing community of researchers who are joining the Leela. This is all of us who are part of the proposals, who are part of white paper writing, who are part of giving talks, etc. The review that we got from NASA was optimistic that a lunar GW observatory would leverage the tremendous resources currently being directed by NASA towards lunar exploration, right? So we have a sort of we know that we are marching in the right direction where the agency's priorities are now being driven. We also have NDAs with two major space companies who are already working on landers. So that gives us a perspective of what can work on the moon and what cannot be sent on the moon, at least as of now, right? And we have some discussions with Israel. I'll come to that slide in a bit. I won't go through, but this is our steering committee. We have those who are part of the gravitational wave community would know several of the names here from various LIGO, LISA, Virgo, Einstein telescope collaborations, all of us who are trying to think about what technologies that can be adapted existing already in context of a moon-based gravitational wave detector. So I serve as the PI of this project, but it is significant, about 40 people working on different components of this experiment. We held our first Leela meeting actually only last year at Vanderbilt. We invited for the first time not just the gravitational wave community, but we invited all the major space industries. We invited the different divisions within NASA that work on the lunar exploration and the human spaceflight program. We also had ESA and ISRO in attendance. It was a very nice opening plenary talk that Kip Thorne gave at the start of the workshop, in which he mentioned about this 1968 workshop in Seattle, where they went thinking that the first source of gravitational waves would be supernova, and came back from the meeting confirming that no, it is actually binary, like a binary black hole or a binary neutron star. In the same meeting, no one had thought about what a space-based gravitational wave detector would be, and came back with the idea which became the LISA mission. So where we are right now, it's a kind of, the trajectory is that we are proposing a detector that is as fundamental as what, those kind of previous studies have shown. We had a very extensive discussions at the Space Applications Center at ISRO earlier this year, where we are thinking about, the potential Leela technology that we can already do in Chandrayaan-4 that is about to be launched in a year or two. Also, the handle they have on precision landing in the context of Chandrayaan, if you remember, the landing was absolutely accurate within the error bar of where they wanted to be. That's something is very crucial for the Leela end station. So all the three end stations have to be very perfectly placed if they're individual launches. So that is a ongoing discussion we have had with them. We also had several discussions with different geoscience communities. So here, at least in India, the National Geophysics Research Institute in Hyderabad, we hosted this whole one-day meeting thinking about what are the different goals that we can have with them. And so is also the University of Paris, which is the co-PI on this experiment. We are thankful that, we've been now considered as the equivalent of the next big missions in our field, which is LISA. In fact, Science had this nice article in which it said that scientists have two ways to spot gravitational waves, two ways being LIGO and pulsar timing. And here are some other ideas where LISA and Leela were both put together as a sort of, what are the next avenues of measuring gravitational waves. I also like this article, the feature article that said The future of cosmology is 239,000 miles away, but closer than ever. So this is a good sort of feedback we are getting also from the larger, broader community. I'll rush towards this part on the policy because it's a question came up. The IAU has, International Astronomical Union, has officially recognized that the protection of astronomy from the moon has a particular urgency. And there is only, if there's a broad class of astronomy you can do, but you can say the two flagship are, you can do radio astronomy on the moon from the far side, which allows a certain 21 centimeter cosmology measurements. And you can do gravitational wave measurements like the one that I described, both of which are not possible if you have Earth-like traffic up on the moon. And so there is a new working group that has been formed. I'm part of this working group, and we are writing a report that will be submitted to the United Nations and forming a sort of a global policy on what to do and what not to do when private companies go to the moon. Right? We don't want like an ad of Nike looking at the moon when we see that at late night, right? The preliminary target, and take this as a sort of where we are right now and what we are trying to aspire. We are at a stage where we are doing pre-formulation and tabletop studies. Those are being actively pursued in several universities, how we would have the current technologies be working in the context of the moon. Just context of what other things are going to happen on the moon. In 2026 will be the first Artemis crew landing. That will be the first time since 1972 humans would be landing back to the moon. And then you have series of landing, each one of them adding more complexity to what the humans will be doing once they land and what kind of infrastructure will be built when they are around them. So our target is to have a Lila Pathfinder mission sometime within this decade, right? That is very key for us to demonstrate the technology. And of course, my personal goal is to have the sub-Hertz gravitational wave detector operational in the same time scale as the space mission LISA, so that it allows us to make these multi-wavelength gravitational wave measurements. So of all things, we need your expertise to help us build the case for the Lila detector, especially the theorist here. I'm also a theorist, so don't get frightened by the experimental complexities here. We want to make several cases of investigation, like what is a unique test of GR? Gopu and I had this great discussion on several of those, which is unique that you cannot achieve in space or on Earth. What is this beyond standard model test that you cannot perform with particle physics accelerators? You cannot perform with gravitational wave detectors on Earth, but you can do with this mid-band detector, right? So it's still being pursued. And the same is also true with instrumentation and understanding the lunar environment. But specifically to highlight here is the test of GR and the beyond standard model physics. We are writing a white paper, and we'll welcome your expertise in helping us write a white paper that serves a broad community. The goal is that by the time 2030 decadal survey comes in, this should be seen as a flagship multi-messenger mission that the community has put forward. So we do want to serve as many science goals and cases that we can. Please scan the QR code or go to this website, Vanderbilt Lunar Labs, and there is enough information about the weekly calls and different organizational things you want to be part of that you can. Final thing to highlight is we have an upcoming meeting in France. In case you are coming to the LIGO Virgo Kagra meeting, which is, we timed it right around that days. We have this meeting in France in this Belle Isle. It's going to be my first time too, but it's this island of the south of France. This is how the picture looks. University of Paris is the host. I'm very thankful that it is this location and not a city. But this is an open invitation, so please, sign up if you're interested to come. But as a conclusion, there is an urgent need to plan a gravitational wave experiment that can access 0.1 Hertz to 10 Hertz, which you cannot do from space or you cannot do from Earth. No modifications that you do to current gravitational wave detectors, LIGO India, future third generation detectors, can help you achieve this frequency range. It's just fundamentally not possible to build this kind of gravitational wave detectors on Earth. No upcoming space missions can do this, at least till 2050s. So if you eliminate all the choices, you are left with thinking about a detector that is feasible on the moon. So we have this rare opportunity as a field that we can take advantage of the fact that humanity is right now, or the nations are very interested in going back to the moon, and how we as a physics and astronomy community can partner them and make this whole endeavor a little more than just adventure and contribute to science. All right. Well, thank you. You've been very kind.
Thank you, Karan. Amazing talk. We are fairly confident that we should be able to pull it out in the next decades. And the science looks amazing, and especially on the multi-messenger. So, and it looks like a Woodstock, since you're talking about musical festival. The audience, the number in the gravitational wave, looks like a Woodstock for me. So, questions, comments. So.
Hi, thanks for a great talk, first of all. You talked about the seismic noise, inherent seismic noise and the comparison of that on Earth and Moon. Is there a particular reason why Moon is so seismically quiet? And if there is, what about other planets in the solar system?
Yeah, no, that's a great. I mean, from what I've been told by planetary geoscientists, is that the moon may be the quietest thing in the entire solar system. And I don't know the first principle reasons why we are so special to have access to a satellite like that.
Thanks. What about the temperature variations?
Yes, that's a great thing. I mean, we have to be very selective of the site where we can make this perform in ways that either we avoid lunar night a lot or we avoid lunar day a lot. It is unlikely right now that both the terrains are operatable at this point, unless and until the kind of infrastructure and battery management that they will be doing for the humans who will be staying there long enough and also going through the same problem, if that solutions exist. Otherwise, we'll be operating in only one of the half of that.
Yeah, so that's a big limitation.
It is a significant limitation, but it is a limitation that impacts everything that we do on the moon. That all the landers, and the fact that the key science or technology goal right now is how do we survive lunar night. It's a major sort of effort that is already being done. But it does not impact us minus the challenge. If we have some way to keep our instrument thermally stable, then there is no in principle problem.
I can.
Thanks for the very nice talk. So I was just wondering, so when you're going to these lower frequencies, and what would be kind of like the data rate requirement?
Oh, so yeah. It is. So actually, the LISA is a good example. It's like in this ranges of hundreds of kilobytes per second, data rate. The moon would be somewhere in that to about something about a megabytes per second data transmission rate. It is not too crazy high, unlike the ground-based detectors, which needs a kilohertz sampling rate.
15 or something.
Yes.
Thanks.
I think it's a question.
Yeah, I have two questions. The first question is, what would be the cost of this project? And where would you expect the major funding? Which country or institutions?
Where would I expect the
Major funding.
major funding?
And what would be the cost? Yeah.
So there are two costs. There is one is the cost to build this, and the second is to cost to send it to the moon. And the two, I have to separate it out because right now sending to the moon seems to be, the more daunting challenge. But in the same capacity, if you want to build a gravitational wave detector on the Earth, making tunnels is your biggest expense. So is it as expensive as making the tunnels? And the idea is no, actually, if you scale it to 2030, the entire thing can be shipped to the moon within like under $50 million. Now, once we have that, how much does it take to make this gravitational wave detector? It's hard to tell. What is the space? I mean, we are at a very pre-formulation stage to give a number on what it will take it to be space flight launch ready. But it would not be as much as it is to build a gravitational wave detector on Earth. That I can be very sure.
Okay, my second question, as you know, the space weather events, extreme space weather event affect satellites.
Yes.
While, designing this, is there any consideration of that? You keep in mind space weather events, extreme space weather events that can derail, satellites, other things. Okay.
Yes, I mean there could be solar storm, like
Yeah, I'm talking about solar storm.
yeah, which is
Like,
which is a thing for all. I mean, Lisa would suffer more, if not the same, as a moon-based detector would be, and yeah, that some level of radiation shielding is just we have to engineer in it.
Yeah, thank you.
Thanks for the talk. And thanks for letting us know about Leela. So you said you were interested in white dwarf binaries in the gravitational frequency of 0.1 hertz. So that must be in the inspiral phase.
Yes,
Uh,
it's in the Roche lobe already. It's in a very late merger stage.
It's in the very late merger stage.
Yeah, so for white dwarfs, because they have already formed that common envelope around them, right? So they're not point particles, unlike neutron stars.
For neutron stars, as they merge in the kilohertz band, can't we study about their Roche lobe phase in the the current gravitational wave detectors?
I don't think that the neutron stars ever have that kind of a puffy exterior to allow this kind of a mass transfer between the two objects, unless they reach, this very late in spiral state. Versus white dwarf, the radius is so larger that it allows a certain interaction to take place. But I'm still not the expert here to comment more on.
Just to add on to that, Karan is spot on. So the white dwarfs will have roughly the size of the Earth. Neutron stars collabor. So when they do kind of touch each other during the late in spiral, that fraction is very tiny. I think they may not last for a millisecond or something like that. And then it merges, and then whatever gamma ray burst or whatever happens. So, but he will still have white dwarfs sort of because he's going to see this up to 100 megaparsec and all that. So there will be several collision of white dwarfs, and that's the game they would like to measure, and they will be able to get the chip. Yes, it is still in spiral, but the problem is that they are not point particle like the black holes or neutron stars, like LIGO sees. So they have astrophysical, the environmental effects will have to go in. So the templates will be interesting to make.
Yes.
Correct. Yes. Yes and no. So black hole neutron star can be very interesting depending on the equational state. The neutron star can be chopped, and then it can actually thrown out into a higher orbit, comes back, and all that thing. That will not happen here because it's not. But it can happen for a IMBH with a white dwarf, for example. Yeah. The first merger may not work. It will be tightly chopped and against and all that thing. Yeah. So it's a complicated. We can talk.
I not understood what is the exact role of moon crater.
The role of the moon crater, the fact that after 2 kilometers the moon's curvature takes over, so you can't have the straight beam without touching the surface. So you have to build around a crater where there is already natural line of sight.
Questions come.
So in that photo which you shown about the CMB being the border, so I just wanted to know where does nanohertz fit in this
So
using
it's
PTA?
inside the LIGO.
It's inside the LIGO.
Yeah, I mean, I don't know how it does not go beyond redshift 1, right? It will, yeah. But
Thank you.
So you have no further question. I have a question.
Sure.
Oh, okay.
So when you have such a large, volume that you're observing, and you can observe for months before the event occurs. So is there a number statistic on how many of these simultaneous superposition of multiple targets you will be seeing, and you have to disentangle them?
we don't have that in context of Leela, but we do have it for Lisa. That is one of the essential data analysis problem, that all the signals in Lisa would be overlapping because it covers such a wide spectrum of galaxy collisions to white dwarfs. So everything would be stacked together. In fact, one of my postdoc has developed this global fit to actually solve for each of those sources together.
But you don't expect that to be an issue for
It will be this 100 and thousands, they are not very common black holes, in terms of their number count. The tens are, so maybe Einstein telescope and others would have overlapping signals.
Thanks.
So you're doing kind of a tomography to kind of dig and then figure out what's.
Yes.
Is that what you're saying? Yeah. So maybe we'll chat about it. So there have been suggestions that there can be wide dwarfs of super Chandrasekhar mass. So it will be interesting to see whether Leela can actually, because we will get the mass estimate. So it will be a very good idea to see whether there can be presence of the magnetic fields and other things. So, whether it can be uniquely used to get the mass of a wide dwarf above 1.4. So that will be an interesting.
That would be interesting, to see how far we can actually.
Exactly. And so we'll chat about that. Thanks. Okay, one more question, sir.
I wanted to talk about EMGW. So since the operating range of this is looking at different kinds of stellar objects of bigger masses, would there be how would we form a network with optical, radio, or X-ray telescopes, or do we just want to focus on the GW physics?
No, we absolutely want to focus on all of the sides of electromagnetic follow-up. For example, an IMBH plus white dwarf could be this X-ray flares that we see, and that is possible. I mean, the only thing would be that we would predict it when it is going to happen early on, just in the same case as binary neutron star. We can predict when the kilonova is going to happen.
Also, a follow-up question is, would this be like a trigger for other telescopes to look in that direction, or would it be like a survey instrument?
It's for a lot of them, it would be a trigger, like all the classics like binary neutron stars, white dwarf, that would be something you will know long enough to send out an alert for that.
Also, like in Lisa, we expect like events to be like longer. So the data acquisition time is quite long. So how would how would communication with other telescope go for this kind of events? Like let's say it takes 1 day of observation to confirm that there is some sort of a gravitational wave there. So how do we?
No, it's an interesting problem. It's definitely something in future we have to figure out. Right? It would be that maybe we do something locally every hour, do the data, and then send out from Earth. It will be set by what is the data transmission limits we have on the moon.
Thank you.
So just a final question. If it's only going to operate during lunar day and things like that, so there will be data gaps, right? Yeah. Naturally. So you guys are thinking about how much that can deteriorate?
I do want to clarify. So as much as I think it's challenging to operate in both the regime, the ideal detector should be doing that. we should not be having the choice.
Okay.
It seems, at least from the initial Pathfinder or tech demo, that we may be limited by picking only one of the two.
Okay.
Right. So, for example, for radio, they like to have it operational at lunar night so that the instrument's self noise is not coming in.
Precisely.
Versus if we want an active measurement, I mean, active, laser power and stabilization system going on, then we would have to operate at the lunar day. And that kind of trade-off is still something that will be studied over the time.
Okay. Thank you very much. I think, again, let's thank Karan again for a fantastic talk and wish you all the best. And I'm sure that we are going to hear, from him many, many more times in the coming decades. Thank you very much.
With the P outside, though.